Hey guys, wanted to take some time to talk to you about the BGP finite state machine. We need to address the states that BGP goes through. When we implement this in the real world or we implement this in our lab, we really need to understand what's going on under the hood with BGP. We need to know all the requirements that BGP needs in order to fully establish itself. And if we don't understand this, then when we sit down in our lab and we get a troubleshooting ticket that says maybe, these two neighbors aren't able to peer or form an adjacency using BGP, we're going to spend way more time than we should trying to figure out why. And believe me, that is not where you want to be. So let's go ahead and let's take a look at this. Let's dive in and let's see what's going on under the hood with BGP. So the very first state that we enter in BGP is called our idle state. So we've come into our device, our two routers, we've said router BGP with our autonomous system, and then we've entered in our neighbor command. So neighbor, destination IP address, and then we've entered in the remote AS of our neighbor, right? But let's ignore that remote AS for a minute. Let's just focus on that destination IP address. So we've said neighbor, destination IP. When we hit enter after that neighbor command, we enter the idle state of BGP. We're going to attempt to establish a TCP connection using port 179 with the neighbor that we've entered in that destination IP address. So 1.1.1, whatever it may be, I'm going to try to establish a TCP connection with that particular destination IP address. Now, at this point, once I've attempted to initiate this connection, I'm going to back off and I'm going to be a passive listener, which means I'm going to enter this connect state. And I'm going to wait here in this connect state for 120 seconds, which is my connect retry timer. Now this timer is hard set in BGP. We can't change it. There's no hack. We're going to have to sit here for 120 seconds. But don't miss what I said. At this point, we only care about the destination IP address in our neighbor statement. We're not concerned with everything else in BGP because all we're worried about is forming this TCP session between these two neighbors. So again, idle state, I attempt to establish a connection with you and then I back off and I become a listener. I wait for you or any neighbor for that matter. You're going to do the same thing. You're going to first try to establish, and if I'm in the connect state and I'm listening and we've fired up this neighbor router, you've tried to initiate with me, I'm listening, we're going to go ahead and start a TCP session. If we have a problem at this point, it's going to be with TCP, and we have to understand that. We could have some control plane policing. We could have a quality of service policy in there. We could be dropping TCP traffic for some reason. We could have an access list. Now, there's a number of different access lists that we could apply that can break BGP, and we're not going to get into that in this video, but just be aware that we're troubleshooting TCP. So we need to look at TCP-related issues. Did I even enter the right IP address in my neighbor command? That's about all I care about inside of BGP itself. Okay, can I get to that address? If I can get to that address, am I dropping TCP traffic somewhere else, specifically the destination port of 179? Maybe I'm not allowed to send traffic to that address. But here we're still only talking about TCP. Now, if the 120 seconds go by and we haven't heard a peep, we haven't gotten any session whatsoever, the next thing that happens is we are going to enter what we call active state. We've spent 120 seconds in connect state listening for a session. We haven't gotten anything. We haven't heard anything. Now we're going to actively try to initiate the session for 120 seconds with that neighbor, with that destination IP address. We're not going to wait. We're going to actively try to establish it. So now we're going to be the speaker. Now we're going to try to do this for another 120 seconds. And if we fail, we're going to go all the way back to idle state. We will go through these three states in an endless loop forever until we fix our TCP problem. So what we need to do, and what I do in my mind, is I draw a line right here and I say that these first three states are considered phase one and they are TCP dependent, Okay, so these are TCP related or dependent states. I'm not going to look at all the other BGP related information because I only care that I can reach that neighbor, he can reach me, and I'm able to establish this TCP session. Now, assuming that we did have a problem and we fixed it, We're able to establish this TCP session now. The next thing that we do is we enter what's called the open sent state. Now, in the open sent state, this is where we actually start to send BGP related messages. What does that mean? You have all been in the situation, either you've done it on purpose or by accident, where you get this wonderful error message, peer in the wrong AS. Well, why does that happen? At what point are we in the BGP states, and at what point in the BGP finite state machine are we to cause this error message? Well, the answer is we're right here, because contained in this open message, we're now sending each other our basic BGP information. Contained in the open message that I'm going to send you is going to be my BGP ID, my version number, my hold down time, and my autonomous system. If the open message that I send you matches your configuration, you send me a keep alive because you think we're good to go. If you send me an open message and I compare it with my configuration, and I find that the information in your open message didn't match what I have in my configuration, I'm going to send you a notification. That notification is going to signal the teardown of our BGP session, and we're going to go all the way back to idle state. Now, you've seen this before, because when we get this error message, peer in the wrong AS, what happens? We get these error messages displayed in our CLI. There's a brief pause. We try to enter the commands to no neighbor, or we try to shut down an interface, and all of a sudden, boom, the error messages come back. We get the same display of errors all over again. And then there's a brief pause, and maybe we try to turn off console logging, and boom, there's another set of error messages. The reason is because TCP is not broken, BGP is broken. So what's happening is we're going back to idle state. We don't have a TCP problem, so we immediately establish a TCP session. We go right into open sent state, and then the minute we receive those open messages, boom, we fail, we go right back to the beginning. Okay, so this is where we actually find that error state in BGP. It's the transmission of these open messages that are going back and forth between our two neighbors. Now, assuming that we don't have that problem, assuming that everything is configured properly, right? So I'm in the right AS, you're in the right AS, we've done our job properly as CCIEs, right? We don't have any issues. The very next state that we're going to enter is called the open confirm state. Now, in the open confirm state, all we're waiting for is the receiving of each other's keep alives. So we've gone past the open sent state, we've sent each other open messages. Your open messages match my config, my open messages match your config. Immediately I send you a keep alive, and you're going to send me a keep alive. During this keep alive transition, we're going to be in open confirm state. Now, if we fail, if I don't receive your keep alive or you don't receive mine, we go all the way back to idle state and we start over. If we receive each other's keep alives, which we should, I mean, there really shouldn't be any problems at this state that would keep us from receiving our keep alives. The minute that happens, we enter the state we want to see our BGP neighbors in, and that's going to be established state. Now, in this state, this is where we will send our update messages. At this point, only in established state. Am I going to send you an update message that contains all of my attributes? Maybe I've set the local preference or the weight or the MET or any of these other attributes. In the update message, that's where these attributes are going to be applied. And not only those attributes, but also the prefixes that I'm actually advertising to you. So I will send you my update message with all of the BGP related config that I'm supposed to send, and you're going to send me the same thing. Now, by default, our keep alives are going to be sent every 60 seconds, and we're going to have a hold time of 180. Now, we can change this if we want to, but by default, we're going to have 60 and 180. Let's go for a minute now. Let's actually check this out in a packet capture. I want you guys to actually see what I'm talking about. I don't want you to take my word for it. You should never do that. You should always validate everything that an instructor says to you. So, notice in our packet capture, these were two neighbors that I had set up. Just router 1, router 2, they were directly connected. I didn't cause any TCP problems because I wanted to just show you that it is TCP related at first. Okay, so notice what we have here. We have router 1 as my initiator. We have router 2 as my listener. And how do I know that? Aside from the fact that Wireshark tells me my source and destination, well, I see here that my initiator, which was my source, had the higher random TCP port number. And in this case, it was 24650. My destination port was 179. So this is a TCP session. The protocol I'm using, TCP, here's my TCP three-way handshake. So again, just regular standard TCP. Once I establish a session, once we have our three-way TCP handshake, router 1, he's the initiator, immediately sends an open message. And like I said, look at what is in the open message. We have the version, the AS, the hold down, and the BGP identifier, okay? So this is contained in my open message, and if you look closely, we have another open message right underneath, and here's router 2. Here's my version, here's my AS, my hold down, and my BGP identifier. So we have this transition of open messages going back and forth. But notice what happens. Router 2 immediately, so here's router 2, my source, my destination, here's router 2, a BGP message, he sends a keep alive. So according to router 2, the update message that he received from router 1 matched his configuration. So we know that the configuration on router 2 must be okay. But look at what router 1 did. Router 1 sent a notification message. We have router 1 to router 2 notification. And what did router 1 say? Router 1 told router 2, hey buddy, you're in the wrong AS. So at this point, looking at this packet capture, I know that the configuration problem is on router 1 because router 1 received the update message from router 2. He looked into his configuration and he said, wait a second, your open message said that you were in AS2, but I'm configured differently. In this case, I know that he was configured in Autonomous System 1. So router 1 was expecting iBGP, whereas router 2 is expecting eBGP. Now I know that because I configured it, right? But the point is that router 1 was the guy that had the wrong configuration, or he had a different configuration. We could have misconfigured router 2, of course, in the wrong AS. But the guy who was misconfigured was router 1, and router 1 says, hey, I'm being told that you're in a different autonomous system than the one you're actually configured in. So his neighbor statement had a different autonomous system. At this point, the BGP session is torn down. Let me shrink this, and you can see that we start over. So we close TCP here, and notice that we start over. So we start over again. Here's our three-way handshake. We have an open message. Immediately, what are we delivered with? We're delivered with another notification message from router 1 that says, you are in the wrong AS. Here's our notification, again from router 1. Let's scroll down, we're going to see another one, again from router 1, the same notification. And look at, if we scroll down here, you're going to see them again. Here's another one, here's another one. This will go down in an endless loop until we fix it. BGP will just continue to cycle over and over and over again until we fix it. So, I obviously went in and fixed it, otherwise this would be a short video. I went in and fixed it, and when I fixed it, I went ahead and said redistribute connected because I wanted BGP, I wanted both routers to not only establish a peering, but I also wanted them to redistribute all of their connected interfaces as well as their loopbacks so that we could actually see these update messages in our capture. So let's take a look at this actually working. So here's our three-way handshake. In this case, it was initiated by router 2. So here's our three-way handshake, and then immediately router 2 sends the open message. So here's the information again from router 2. Same exact information. If we go down and we take a look at router 1, we have this same information that we had above. So they're the same open messages. The difference is that we've fixed the neighbor statement on router 1. We've gone in and said neighbor IP address of router 2, remote AS2. So we've put it in the right AS. Immediately after we have this exchange of open messages, we have the exchange of our keep alives. Once we've established and once we get the keep alives back and forth, the very next message that we see is the update message. And in this case, the update message is being sent from router 2 to router 1. And look at what we have. Just like I told you, we have our network reachability information, the NLRI, which is essentially the prefixes that we're advertising to our neighbor, in this case router 1, and we have our path attributes. So in this case, we had our origin, our IS path, etc. So these are all contained in the open messages. Look at router 1. If we scroll down just another packet here, router 1 sent the same the same update message saying here's my prefixes and here's my path attributes in BGP. So this is the transmission of these open messages in these update messages in established state. If we advertised another prefix, we would see another update message. If we removed any prefixes or applied any filtering, or we applied any extra BGP attributes, we would see those in an update message. And this is going to be happening in our established state. And if you scroll down, we should see, well, I stopped the packet capture, but again, we see these different keep alives that are going back and forth. So don't allow yourselves, let me erase this, don't allow yourselves to get confused with regards to the BGP states. We have to understand this. The first three phases, or states rather, that BGP goes through, we can consider that phase one. We can consider that TCP phase. That's where we're going to try to troubleshoot or have our requirements to implement BGP. The second three states, that's going to be phase two. All right, very, very easy. And in phase two, we're going to care about BGP. We're going to be looking at BGP configurations, BGP related information. So don't allow yourself to get confused. Make sure that you pay attention to this. Make sure that you read the RFCs. Make sure you study hard, guys. You have any questions, please reach out to me. Let me know. Keep up with your studies, and I hope you enjoyed watching this video. I really hope it was informative. I'll talk to you soon. Bye-bye.